So I hope now that you can see
Yes.
my slides. Yeah, so I think Maxim's talk was also a nice introduction. So we've seen trusted AI's importance if you work with neural network. And that's what I wanted to show you in my talk, explaining deep neural network decisions for secure verification. My name is Peter Eisert. I'm at Fraunhofer HHI, and I'm also professor for visual computing at Humboldt University. Yeah, and I wanted to give you in my talk some examples where we use explainability and interpretation methods in order to make detectors on attacks on face recognition systems more robust. So we use face recognition and verification technology in different various tasks, as you see here. And we have already seen in the previous presentation that there are many different threats on such systems. For instance, there are these face morphing attacks where you can have multiple identities. At the same time, presentation attacks where you show a different identity. Or deep fake attacks. And we are working with all these different types, trying to find detector solutions to find out if there is an attack. And and I want to show you in this presentation that explanation is very important in order to make these solutions robust and robust also against future attacks. So presentation attack as a first example, here you show basically an image or a video to a camera with a different identity, or you can just change your own identity by wearing some mask or adding some accessories, makeup, and so on. And the difficult question now is how to detect such kind of fakes and attacks, and we have addressed that in the BMBF-funded project 3D Finder by analyzing different aspects and fusing multiple detectors to come to a decision whether this is a real face or a presentation attack. So one example that you see here that we have worked on, so we analyze blood flow. This can be done easily by small variation in the color. So pulse measurement is state of the art. We also extended that to have a spatial distribution of blood flow in the face, and then we can have some detectors that find out whether there is a person wearing a facial mask, because this occludes also the blood flow, and some partial mask or full mask could be detected. Other cue might be the geometries, because a face has a certain geometry, and by pointing up a tablet or a picture, this has a different geometry. So we used also 3D sensors in order to analyze these kind of attacks. And we trained some deep neural networks, and they were very successful, worked very nicely. The problem is that we don't know actually what these neural networks do and how robust they actually are towards unseen events. The same holds for face morphing attacks. We have seen them. You can take two images and create a face morph, and then both individuals can use the same identity card for passing, for example, through an e-gate. And the problem with that solution is that it's very easy to create such kind of face morph. You can just align two images and then blend them to create an intermediate view. Or you can use now, similar to deepfakes, GANs, which synthesize faces. So for instance, this is a face that we have synthesized from those images such that they are biometrically similar to both originals. So now you have to analyze whether this is a fake or not. As already pointed out, we were part of this Ananas project, and we are also doing similar things in the European initiative D4Fly for analyzing face morphing attacks. And in the simplest way, we can just take the images and do a blind detection of face morphing attacks. So we trained deep neural networks for recognizing such kind of attacks by looking at small artifacts in the images, and they were very successful. So we had equal error rates of 3%, meaning that with 97%, a criminal gets caught or detected. Yeah, and that's nice, but again, the question is how good are these detectors? And actually, we don't know, because these deep neural networks are, as we have seen before, black box systems. So we put in some images and we get a decision out. And although these deep neural networks are very successful and can provide solutions that sometimes are even better than a human classifier, the problem is that we get an output without an explanation of this output. So the question is, can we trust that output? And that's a difficult question. For example, if we have to hold back a person at an e-gate, that shouldn't happen without any reason. So some kind of explanation and interpretability of the solution would be beneficial. And at HHI, our colleagues have developed a method for explaining deep neural network decisions, which is called layer-wise relevance propagation. And this is a method where you first run on your already trained neural network, you run a forward pass providing an image, you get a solution as an output, and then starting from the decision of the neural network with the class that has been highlighted, you back propagate the relevance to the previous layers depending on the activation and weights, and you do that layer wise until you have reached the first layer, and you at the end you get a heat map indicating which pixels in the image were actually important for this particular decision. And this can give you some insight or hint on how the network has actually spotted or come to the solution that a certain decision was reached. And we can now apply this technique also to our problem. So looking at the presentation attack with the analysis of 3D geometry, I mentioned that the test worked very nicely and we could easily detect real face and presentation attack by different kinds of papers, iPads, or other pictures printed on objects. But we analyzed our detector and found out that the neural network did not actually do what we wanted to do. So the network, and this is highlighted here in yellow color, the importance of the image, it looked basically at the silhouette of the objects. And some face has a different silhouette than an iPad that is holded up. But it does not look at the face geometry, which was the intention. So actually this network came to the right decision, but of the wrong reason. So we retrained our neural network by omitting the silhouette information. And then we run the analysis again. And here, unfortunately, it's different color. Red points to a real face, blue tends to be against the real face. And if you provide real faces, you see the detector looks at the entire face region. And if you present some presentation attacks, you get clear highlighting regions of those regions which do not correspond to a real face geometry. So now the detector works much better, and the explanation has helped to improve this solution. And yeah, similar things can be done for the face morphing attack. I mentioned we trained our neural network, got an equal error rate of 3%. And yeah, we used FLRP for finding out what the detector actually did. And yeah, the detector actually looks into the eyes of the face image. And yeah, that's not very surprising because the eyes in the face has very high frequency detail, so it's difficult to blend and overlay them to each other. You have eye leashes, which are difficult to align. So it's very likely that there are some incorrect things within the eyes. So the net detector looked only at the eyes, and that's bad, because now if you are an attacker and you know that, then you can just keep the eyes and fake everything around that. And our detector would then say, oh, everything is fine. So we want to force the detector to look at everything. So we changed our training strategy by providing only small region in the face that were morphed, and all things in the face stayed original. And now we use the multiclass network that was not only forced to tell whether this is a fake or a genuine image, but also to tell which region in the face was faked. And then we removed the last part and retrained everything again to get the binary decision out. And now the detector looks at all region in the image and can be much more robust. And this is also shown here. So we trained our, or we tested our detector. So with the old naive trained detector and the multiclass detector against our genuine and fake images. So both had around the same classification rate of around 3%. And if we presented them only partial morphs, then the naive approach breaks down completely and the other is much better. And yeah, of course, this is not astonishing because this one has also seen these partial morphs. But if we apply completely different attacks, for instance, a gradient attack, an adversarial attack where you add some noise on the image, then you can see, although this detector has never seen this kind of attack, it still gets a robust solution while the original naive approach breaks down. So being robust against one additional attack helps also towards other attacks. So LRP helped us in both cases for getting the solutions more robust, but we also want to use explainability not only to the technical expert, but also to other people, for instance, a border guard, control, and there we need something more plausible for visualization. And one thing that we found out that LRP is great for analyzing what happens actually within the network, but it's not always very simple to analyze because these neural networks are very complex systems. And for our multi-class network, we've found out, for instance, if we change one eye, actually the other eye was highlighted as being manipulated. And that's very strange. But analyzing the network, we found out that this classifier actually tries to compare both eyes. So this eye, the other original eye, is also important for the decision of a face morph detection. And depending on the structure, it could highlight either or the other eye. And this is, of course, not helpful to a non-technical aspect. So we created a different enhancement of explainability. And looking at the neural network, we have often structures that are convolutional, which where each feature corresponds to a specific region in the image, and then you have a classifier that does something weird. And we have built an explanation technique that only works on the convolutional part, where you have a much higher correlation between one point in the feature layer and the original image. So a mismatch of the eyes cannot happen. And if you run that kind of explanation on face morphs, we get, in most cases, a very similar result. So this is the result of LRP when a face morph is shown, and so there are some artifacts in the eyes and the highlight on the nose or here in the mouth corners, and FLRP works basically the same. But if the classifier is a bit unsure, so the decision is on the boundary, then LRP does something maybe inconsistence, for instance, highlighting this eye, which looks okay, while FLRP now shows all the artifacts in the image that could hint to a face morph. And this is much easier to interpret compared to this decision. Yeah, and with that, I would like to summarize the talk. So I've shown you a couple of examples where explainability has helped to improve detecting face morphs or presentation attacks or deepfake attacks. So explanation, I think it's a very important toolbox, although it cannot explain everything, but it's getting more and more robust. But it provides you some hint about a possible solution of the output, and that's an important task, especially in this security-related application, where the decision of a neural network might have some consequences to other people. And yeah, with that, I would like to thank you for your attention, and if there are some questions, I'm happy to answer them.
Thank you, Professor Eisert. I think that was a great presentation. Even if you are familiar with the topic, it is always interesting to see what can be done with current technology. So